you just check CP has no 0 columns. So in a typical control system software, you'll say, okay, here, give me A, and it'll tell you it's observable or not, because it's going to do exactly this for you. It's going to give you, actually, it says, give me A, give me C. And say, yep, observable, great, you're in good shape. Okay, and or of course, you can also do this. So these are two techniques that we can use for observability. Again, why it's true is beyond what I want to get into. Controllability means something else. So let me write down controllability. And now I'm out of space. So I'm going to, can I erase this over here, observability? Okay, so observability, basically, the criterion is intuitive, and then the actual, mechanical process of checking it is even simpler once you know some linear algebra. And then controllability similarly has the same kind of form. Controllability so let me read the definition and then explain what it means. So controllability says that a system X, a system state, system state X0 is controllable. Okay, so we're talking about a particular state, okay, controllable at time t, okay, if there exists a piecewise linear continuous u as input u. Okay, so we over in, so again we have a 0t. So we're starting with some state 0, and we have some time horizon t, and we're going to give it some input, okay, so far, which is all I said is I'm giving some input u, which is piecewise linear continuous. Okay, so this is controllable if, okay, so if there exists something such that the system moves from X0 to desired state X d t at time t. Okay, so I have some input, I can get it where I want it to be. Okay, if I can do that, it's controllable. So imagine there's this bowl with the marble at the bottom. Okay, that's X0 is 0, and I want to say, okay, at time 5 seconds, I want it to be, halfway up the side. I'm going to move it halfway up the side. And can you do it? You say, yeah, sure. If I give it a particular command input, it's going to roll up all the way, and then I'm going to move it up there. Okay, great. That means the system at 0 state is controllable at time t at that point. Okay? Yeah?
Do you have to specify the desired state when you ask if it's controllable, or any desired state?
Any desired state. I can move it from the 0 state to anything I want to say. Go there, go here, whatever. If I can get it to anywhere I want it to be, I'll call it controllable. Okay? And then if every input state, every state X0 is controllable, then we'll call it completely controllable. Okay? In the same way, by the way, if every input state is observable, then we call it completely observable. Okay, otherwise it's observable for that particular input state. So, okay, so this is controllable, and if every state is controllable, it's called simply controllable. And this is going to be true if, similarly, we have the test. Instead of having the column matrix like this, we're going to have this matrix, which is going to be B, AB, A square B, A to the n minus 1, B has rank n. This is a similar criterion. And the criterion for the controllability is A has distinct eigenvalues, and P is the same singular, P is a non-singular diagonalizing matrix. Then instead of having CP has no 0 columns, we're going to say that P inverse B has no 0 rows, has no. Okay, so it turns out that if this has rank n or P inverse B has no 0 rows, if either of these conditions hold, then it's going to be completely controllable. Again, you can see it's sort of a plug and chug kind of thing. We have a system, we know we can figure out P is from the eigenvalues. Once we have the eigenvalues, we can determine that if they are unique. If they're unique, we do this. If they're not unique, then we compute this, find out the rank. And if the rank is not n, we say, oops, sorry, it's not controllable. Okay, there exist some states that can't be reached from the input state. Okay, so I'm going to try and give you a sense of what this means, and then we'll go into controller design. So we have a system now given to us as a black box. Okay, let's say you are driving your car, and you press on the accelerator, and the car moves. Okay. You actually have no idea how it's happening. Okay, all you know is when you press the pedal, it goes faster. When you take the pedal, foot off the pedal, it goes slower. So it is a black box. We don't know what's going on, right? Presumably, it has some internal state. Okay, and okay, now what we're going to tell you is that we're going to give you something very, very important. We're going to tell you that it's in this case single input, single output, because the accelerator pedal position is your input, and the velocity of the car is the output. So it is single input, single output, but the manufacturer is going to come and say, hey, you know what, this is the state equation. I'm going to give you these equations, AX, BU, FW, etc. So it's giving you those equations. It's a very, very important criterion, because you open up the owner's manual and it says it's a black box, but it's not really a black box. It's a black box which has these equations. Okay. Now what you can do is you can take those equations and basically do some linear algebra, and you can say, look, I can tell you it's observable and controllable. And actually what this means is that by observing the output and the command, I can tell you exactly what the initial state was, whatever the internal state is. Okay? The internal state may be something completely arbitrary. It could be some valve position, it could be some storage of some gas in some reservoir, or who knows what. Okay? It could be some turbo thruster. We don't care. As long as it's linear, time invariant, and maybe the 20 state variables, okay, that are related in some fashion, and the output depends on this. As long as you have those equations, you can actually observe the initial state, and you can get from any initial state to any desired state if these conditions hold. That's the beauty of observability and controllability. Okay, we can actually completely control exactly what we want the system to do. We just need this set of equations over here. So if the manufacturer gives you the equations, and you have that pedal and you have the output, you can observe it, you can observe the input, you can observe the output. At this point, you can say, okay, I can make this car do whatever thing I want it to do, okay, because I have the equations. Of course, in real life, what the problem is that even getting this is pretty hard, right? And it may turn out to be non-linear, and if it's non-linear, then life is difficult, and then this one is ignoring any delays in the control loop and all this other stuff. It's all hidden away inside the A is the fact that there's any delays and so on. But in the ideal world, it works pretty well. I have a controllable, observable system. It certainly is a good concept to have, right? If there's going to be some elements of the state that are not even observable, then how can I do control based on that? I can't even see what's going on. So then that gives you some idea of how difficult it is, what it is that you can see. Again, from a more practical point of view, when you're writing software, writing a system, what does observability mean? It means that certain code variables are visible or not. So to the extent that you're logging everything, you're making those internal states visible. So that's the importance of writing, to a log when you're writing any software. Just log everything, because it's an internal state variable. So every state variable is potentially an internal state variable. It's going to affect the output. So just put it in a log, and someday you may want to see what's going on. That's what you're doing. Okay, because of course computer systems are extremely complex systems with perhaps hundreds of thousands of millions of states. One could argue, in fact, that every element of a RAM is a state variable. Okay, so if you have a memory of size 20 gigabytes, you have 20 billion state variables. Okay, What's the output of this 20 billion state variables? It somehow seems to work, but from the control theoretic perspective, this is absolutely awful. I mean, think about this. There are 20 billion variables for this, and every 2 billionths of a second, if you have 2 gigahertz clock, right, twice a nanosecond, the state variables can change. And you have 20 billion state variables. So if you went to a control engineer from the 1920s and said, oh yeah, I have the system with 20 billion state variables, and every nanosecond I'm going to change some state variable, every half a nanosecond I'm going to change some state variable, and make sure it doesn't crash and the system is stable. Okay? Because if it crashes, people will say, your Windows crashes or your Mac crashes, and that's not a good thing, you're going to lose sales. They're going to think you're absolutely nuts. Okay? And that's what we expect our engineers, software engineers, to do today. You're going to have this incredibly complex system, your cell phone, and if it crashes even once a year, you say, it's this terrible software, it doesn't work. Okay, but look at this. This is absolutely insane. So we have to use different techniques when doing large-scale software. Obviously, traditional control is not going to work for you. Okay, any questions about this so far? Yeah.
Back to the observability.
Yeah.
So let's say you have your bowl and you have you know that you're not putting any input, so your marble always goes to the middle.
Yeah.
And so, what if you're given that final state,
Mm-hmm.
the marble is in the middle.
Yeah.
And you're expected to trace it back to its initial position. But
Yeah.
there could be multiple initial positions that led to that final
So
state.
observability means you're actually observing both the command input and the output over the entire time 0 to t. And I'm going to tell you what the initial state is, right? There's no magic. I'm just going to roll it back step by step because I know the output, right? I know the inputs. I know the equations. I'm just going to work it backwards and say, oh yeah, it must have been x0, must have been this. It's not magic. You're right. Obviously, there's an infinite number of initial positions. And so we do need this to happen. And in fact, if you don't have observability, there are basically hidden states that we can't get to, and we don't know. It could be any number of one of these initial states. They all lead to the same output. So we have this aliasing problem. Yeah.
It's actually just on this thing, like if we suppose there's no friction,
Right.
then we see the marble oscillating on
Right.
the diagonal.
Sure.
So we know at least 2 positions where could be the
Right. I mean, so if it's not observable, we have many problems. But if it's observable, knowing the state equations, knowing the output, knowing the input allows us to trace it back from xt to say this must have been the initial condition. We can uniquely identify the initial state. That's the meaning of observability. Let's look at controller design again from a very, very high level perspective. So I've given you the system and I say, okay, it's a SISO system, state space, design a controller for me. So before I do that, let's try and recollect what we did in the classical approach. So in the classical approach, what we did was we said, well, we have some command input u, and u is going to be, in the PID case, it's going to be some, KPE, or it's KI, integral E, or it's KD, okay, KD dE by dt, right, or some combination of the above. So what are we trying to do over here? We're basically taking the error and we're going to use the error to tell us what command to choose. Okay, that's the basic idea. And it worked pretty well. But now we want to essentially generalize this idea because what we want to do is that we want to take the u not as a function of the error, but we want to have u as some function of the state itself, kx. Okay, k is a vector, x is a vector, okay? And u is going to be a scalar, so scalar command. Because it's SISO system, so input is scalar, right? We still have a SISO system. So we're not taking it as a function of the error, but taking it as a function of the state. That's the way we do it over here. And it's a constant multiple of the state. Again, that's the kind of the classic, not the classical, standard way of doing control over here. And so if you do this, then we can write this equation, if we ignore the disturbance as usual, we're going to write x dot equals ax plus bu, which is going to be bkx, right? And so it just becomes a minus bkx. Okay. So, okay, so that looks like an interesting equation over here. And the thing is, what can we do with it? Okay. And the way we analyze it is to say, look, this x dot equals a minus bkx, if I draw a box around this one here. And remember, this is not it's a control system. It's not an uncontrolled system. It's a control system because we have bk, which is your u over here. And you compare it with this one over here, which was x dot equals ax. This was the equation over here. If I have this blue box over here, if I compare the blue box and the orange box, they look pretty much the same, except that I've replaced a with a minus bk. Right? That's basically what I've done. So I would argue that the solution to this control system, therefore, is the same, except over here, I'm going to replace the a with a minus bk. Okay? And I'm going to remove all this other extraneous stuff here just to explain what's going on. So I'm going to put over here, this a goes to a minus bk. So x of t is going to be the inverse Laplace of si minus bk inverse this over here. Okay. So far so good. Okay. All I'm doing is just choosing a particular kind of control. Okay. Instead of controlling on the error, I'm going to control based on the system state. If I do this, then I can say that this particular inverse, I'm going to rewrite using the cofactors as L inverse of the cofactor of Si minus A minus Bk this is going to be a transpose of the cofactor, that's the adjoint, over the determinant of Si minus A minus Bk x of 0. Okay. So I've actually done the substitution over here, and let me just draw another box around this to show that this is sort of the result that we want to look at for a moment. And what we're doing over here is that we're looking at the time evolution of the control system. Yes, Danny? Oops, wait a minute. Yeah, so I should be minus, u is minus kx. Sorry, thank you. Minus, yeah. It doesn't really matter which you are, but yeah, it's just a choice of b, right? It doesn't matter whether you make it positive. Yeah, but you're right. To be consistent, I'd better keep negative over here. Okay. So, any questions about this part here, though? I'm just basically plugging in the same analysis as before. I'm just replacing a with a minus bk for the control system. Okay, so let's look at this a bit more carefully. What we're saying is that we have over here some coefficient matrix, okay, and then below, and then here's some determinant at the bottom, and we're going to take this whole thing and multiply with x0, and that's going to be the trajectory. It's going to be the trajectory of the control system. And if you remember last time's lecture, we had on the bottom we had Si minus A determinant, okay, and we had this cofactor over here, and what I argued was that this is a ratio of polynomials. Okay, and if you look at it, again, you'll find that this will continue to be a ratio of polynomials in S. Okay, so this is going to be a ratio of polynomials in S, and it will turn out that the ratio of polynomials is going to be, if you take the inverse Laplace, is going to be determining on the roots of this equation over here, Si minus A minus Bk. Okay, and so this determinant controls what's going to happen to the system. Is going to be stable or not. Okay, so going back to the previous case of the classical control, the system was stable when the roots of the denominator polynomial, okay, which became the poles of the system, were in the left hand of the plane, of the complex plane. Okay, in the same exact way, the roots of this determinant are basically, so this becomes a characteristic polynomial right here, And if we take this characteristic polynomial over here, we can essentially choose the value of k, okay, because k's are control so that the roots are going to be in the left hand of the complex plane, and if that is done, then it turns out the system is going to be stable. Okay, again, I'm keeping it at a very high level. So let's go back and see what's going on. You have a SISO system that's given to you, and we're given some output, okay. What we do is we choose the u over here. Let me erase this because it's not relevant anymore. We're going to choose this u to be minus kx. When we do this, y is going to be what? It's going to be d times minus kx, right? So y is being controlled by this, of course. Y is going to depend on x from cx as well, but okay, we have some knob to see what y looks like. But the choice of k over here is chosen such that this determinant at the bottom is going to be having roots in the left half plane, because you can control that placement of the roots by the term a minus bk. So a we can't touch, b we can't touch, that's part of the system, but k we can. And so the game becomes, how do we choose a k such that we are able to make it stable and we achieve the output that we want, okay? And that's the kind of the whole point of SISO control. And it turns out the system is controllable and observable, those two criteria, then we can actually do whatever we want. We can actually get it to do the right thing, get the desired output, and make it stable. And so the whole of advanced control turns out to be this equation and determining how to choose k properly. Okay, and it's not very straightforward. There's some complexities there that I'm not going to talk about. But if you choose those, you can choose this k. But this is basically what we do over here. And of course, this is a very, very simple proportional control. We can make this more complex, and that makes that more complex. But still, it can be done to achieve our goals. Okay. So, any questions about this over here? Okay. The other thing that we want to do when choosing u, I'm just going to outline a couple of terms that come up when you study more advanced concepts. One of them is we want to minimize the deviation. So we have other goals. So one goal, of course, is to get to some output y, which is the desired output. It's a control goal. But the other goals can be minimize magnitude of state, because that's an internal state. And if you look at that, the magnitude of the state is basically given by xtx. I already showed this to you. So xtx, okay, square root is going to be basically the, it's going to be sigma xi is going to be square root of sigma xi square, and that's the magnitude of the state. To minimize this, typically what we do is to define, we define an additional matrix Q, put it in a Q, and this is going to be nothing more than sigma qii, where Q is typically diagonal, though it doesn't have to be. It's going to be sigma qii xi square. And so we say, okay, we want to minimize this matrix xtqx, and that corresponds to minimizing this over here. And similarly, what we want to do is that we want to minimize the magnitude of the control input, because that's the amount of power and the way you do that is to minimize ut, and this is often called ru, which is basically sigma r ii ui square. Okay, so these two terms xtqx, ut, ru are called quadratic forms. They're called quadratic forms because they're really sums of quadratics in x and u. Okay, so these are standard ways of representing quadratic forms. So anytime you see xtqx or ut, ru, you should immediately think of them as minimizing or representing the magnitude of some quantity with some weighting factor, because this is the weight given to the ith term of the state. So you want to say state 1 has got a lot of values, state 10, we don't care. All right, we'll just set the qi's to be the appropriate values. You're going to then minimize this. So this is a weighted sum. This is another weighted sum of the control input. And then we typically pose the problem in doing SISO control is saying we want to minimize the sum of these two things. We want to basically say minimize xtqx plus utru, and this is what's called linear quadratic control. And that's why we have this funny term, linear. It sounds like oxymoron. Okay, linear quadratic control. Linear because the system is linear, and quadratic because we have these minimizing terms which are quadratic forms. So it's called, and then typically we assume the noise is Gaussian. The W term over here is Gaussian, and that's a very standard control called linear quadratic Gaussian, LQG. So if you see anything that says LQG control, that's linear quadratic Gaussian. So the system is linear, linear time invariant. The minimizations are quadratic, and the noise is Gaussian. And if you, any standard textbook on control theory will say, okay, this is LQG control, and very, very standard solutions that people use all the time. Okay. Last thing I want to, a couple of things I want to touch upon. One of them is how do you generalize it to MIMO? And so this is SISO. So MIMO, basically the B and the K matrices, all these matrices, these vectors become this used to be a vector, and it's going to become a matrix. B, this is going to become matrix. So basically all of these become matrices, and so over here you will this thing is going to become the K matrix, etc. So we can go from vectors to matrices and then do MIMO. Okay, again I'm going to wave my hands a lot about this, and in principle it's no different. In principle what we're going to do is that instead of having A minus BK, we're going to have A minus BK, and we'll do the same exact thing as we did earlier, except everything is a little bit more complicated. But the beauty of it is that the approach still goes through, but it's still linear algebra, still the same all ideas, except that now we can control multiple outputs, have multiple inputs, and have the state vector be as big as we want. So we can have multiple input, multiple output control. And this was really the reason why people went to state space control from classical control. Classical control, you can't go beyond SISO. Okay? And of course, the internal state X is hidden. We don't even care. We look only at the transfer function. Here's the input, there's the impulse response, it's a transfer function. We do the Laplacian, do everything, life is good. And say, oh, I have two inputs, and they interact with each other so that we have a state. The state is going to be affected by multiple inputs. That's why A is going to have off-diagonal terms. Classical control says, sorry, we'll just do one at a time. We'll assume they don't interact with each other. With MIMO control, we can actually take the same equation over here and just convert the vectors to matrices. We studied this in the beginning of this class. And once you do that, essentially the same approach just works. It gets a bit more complicated, but no new concepts are needed. We still do pole placement, we still do the inverse Laplace, we still do this determinant characteristic equation. All these things just go right through, and that makes it very nice. Okay, that makes it much more understandable. Okay, any questions about this over here? I do need to talk about one more quick. Okay, I want to talk about one quick thing, which is what happens in real life, the separation principle, and then I want to touch on digital control. So let me quickly talk about separation principle. So we have a system where, let us say, some state is not observable. Okay, we have some internal state, we can't see it. So what do we do? Okay, and so there's this whole area, what's called state estimation. It's a huge area of work. And in state estimation, what we do is that we estimate what the state is going to be. So remember the web server example. The web server example, we had a web server which had a buffer, and for the purpose of keeping it simple, I was saying, yeah, I'm going to send you feedback all the time telling you the buffer occupancy. Okay, but of course it's never going to be true. No system is going to send you back buffer occupancy information all the time, so you need to estimate it. Okay, so the beauty of this is that the estimation itself is a control problem. It turns out to be very simple, similar to estimation. So what happens is that we have some true system state, and that leads to some output. Okay, and then we have some estimated state, and that leads to some other output. Actually, it should lead to the same output. So what you can do is that you can compare the output and the predicted output and we put this into a comparator, okay, and what comes out of this is the error. It's saying, okay, with this error, what I can do is I can go right back and feed it into an estimator which has the estimator state. So what am I doing over here? The estimator looks a lot like a controller whose goal is to minimize the gap between the actual output and the predicted output, okay? And we look at the error, and so we say, I think the buffer has got 20 packets in it. I'm going to predict that, and if that's the case, then something is going to happen. Buffer loss is not going to happen. But in fact, loss actually happens. So, oops, there's an error. I better go back and fix my estimation because I wasn't okay on that. So we do this, and this loop is essentially a prediction, or it's basically estimation. We are predicting all the time what the internal state variable is, right? And this allows us to estimate the state. From the estimated state, then we can plug this into the actual controller. The controller is sitting over here, and which has some in command and some and some output over here, right? This output actually is the same over here. It has a true state. So what we're doing is we're actually running two control systems at the same time. One of them is trying to minimize the error in the prediction, and the other one is trying to actually minimize the error in the output, actually get the thing to do the right thing in the first place. So we have these two different systems. And when you look at the math, and I'm not talking about it, of course, this system turns out to be very, very similar to this system. In fact, it's a control system as well. And so, as I said, because of these two control systems, we have this typical modern controller will be doing both at the same time. We'll be estimating, predicting, and also doing the control. And so one could ask, what is the stability of this combined system? Okay, does this whole thing actually work? Because you have this one thing going on, the other thing going on, they depend on each other. And we have this very nice principle called the separation principle, which says that the poles of the output that depend on this controller and the poles of the output that depend on this controller are distinct. Okay? In other words, any errors that happen here, any errors that happen there are distinct, and therefore what we can do is that we can separate the two. We can do separate things. So we have an estimation issue, we have a control issue, assuming perfect estimation. And if you build these two together, what will happen is that the overall system is going to have separate poles, and just make this stable, make that stable, and the overall system will be stable. Okay, that's what the separation principle states. But in practice, we have to do something. What we have to do is to make sure that when we make a change to the system from the upper level, the lower level has got enough time to figure out what's going on before the estimate converges. Because what happens is a change happens, it's going to take some time for us to figure out what's going on. Okay, the estimation process takes time. Okay, there's a time constant hidden over here, and there's some time constant hidden over there. This is the loop gain parameter, for example, right? So what we do is this. We try to make this estimation process, again, rule of thumb, very important in practice, try to make this an order of magnitude faster than that. Okay, so if you're going to make a change over here every second, then you should be estimating basically 10 times faster, once every 10 times a second. Okay, so if you're driving a car and you want to you're going to actually predict what the output is going to be, right? You're going to predict the true state. You don't actually know where the wheels are. You turn the steering wheel, but you don't know where the wheels are. So you're going to predict, right? Based on this estimation, you're going to estimate, I guess, where the wheels are going to be. What you need to do is you have to keep track of where the wheel positions are going to be much faster than turning the wheel. So you turn the wheel slightly, check what's going on, get a good sense. Yeah, the wheels actually did turn. Okay, now I can turn it some more and do the control problem. So the estimation and the control are linked, but the estimation should be done faster. Okay, and I'll go back to now TCP. In TCP, what happens is if you're going to take the control action of increasing or decreasing our window once every round trip time. Okay, and the reason is because we're getting feedback with every acknowledgement. That's estimation. That's actually estimating the internal state. We're doing that pretty fast. And then once every round trip time you say, okay, I'm going to make a change. I'm going to increase it or decrease it. If you were to make a change with every packet, it gets unstable because we don't have the, though we do have the separation principle. It is true we can estimate and control separately. In practice, when they have the same time constant, the poles get all mixed up and it gets really messy. You can have a very unstable system. And so what we want to do is to do this much faster than that. So we then rely on the time scale separation. So we want to have basically time scale separation where this is being done on one time scale, this is being done on another time scale, and that's a very important principle in practice. Try to keep the time scales separate and do the estimation at the faster time scale and the control at the slower time scale. Okay, and this is how we build practical systems. So when we do engineering for the internet, for example, people will throw around this term, time scale separation, estimation, prediction, and all these other things. And all of them are valid, but it all comes from this basic understanding that we have actually two control systems going on, and that the poles are distinct from the separation principle, and that we would like to keep these guys at the faster time scale, at least keep 5 times faster, if not 10 times faster. Okay. Any questions about this over here? Okay, how many of you need to leave at 10:20 exactly? Because I want to take a few minutes more. Okay, all right. So I have this thing on digital control that I wanted to talk about, and it's also your homework. Okay, I'm going to give you the solution to the homework so you can at least check that, and then those of you who have to leave can leave, and then I will cover what I can. And then I will fix I will probably spend a few minutes on the next class, which I didn't want to, and then we'll go into probability. So the solution is t greater than 0.5, okay? So that's the solution, okay, for what it's worth. And then let me talk about the, because I do want to get that out of the way. Let me talk about the digital control. So, yeah.
What's the equation for z?
The equation for z is going to be, let me see, so z equals, mod z is less than 1, and so mod 2t minus 1 by 2t is less than 1. So that's going to be the, sorry? Oh, I'm sorry, alpha. What is this? Oh, right, I'm calling it alpha. Sorry, I can't remember what I'm calling. Wait a minute. Oh, it's alpha t, right? So alpha, what am I? Oh, wait a minute. You know what it is? I did it for alpha equals 2. So t greater than alpha, 1 over alpha. Sorry, yeah. Thank you. I did the whole thing for 2 in my solution. Then when I put the question up, let's make it alpha. So I forgot about that. Yes, so this is the criterion for stability, and for z the equation was alpha t minus 1 by alpha t mod is less than 1. Okay, that's the equation. Yeah.
Is t discrete?
T is the time step duration, right? So yeah, t is going to be.
So could you also say greater or equal to 1, since 1 over alpha is between 0 and 1?
Aha, is t greater than 1? Is equal to 1. Yeah, that would be fine because we have t time steps. So t is it's going to be discrete value. Yeah, that's good. Okay. Yes. Equal to. Thank you. No, on the border it's oscillatory. It's not. Just, okay. I think I'm really pushing this too far. Okay, let me talk about this next time. I don't want to for people having to leave. So I'll collect the homework and then I'll actually do the digital control. And then for next class, I'll tell you what we're talking. I'm going to talk about basically probability and conditional probability and joint probability. So next week will be all probability, and then the week after that will be information theory. So.